So in the last video, I found when I first learned this technique, I really didn't like this thing where the teacher was like, "Oh, e to the c, that's the same as a." I hated that when we did derivatives and differential equations, that little so-called trick that I did. So what I want to do is make this a little bit more practical in terms of how we do differential equations in AP Physics. So you notice we've only specified our answer to within an integration constant, and in physics we always provide information that lets us come up with a specific value for that constant. So the other consideration is that we are solving differential equations that are not with respect to position, but the derivatives are taken with respect to time. So instead of primes, you'll notice we use a dot, and what that dot means, again, is a time derivative. So for example, in this case, we have x dot plus 3x equals 0, and we're told that at time equals 0, x equals 5. So what we're going to do is solve this differential equation. In other words, we're going to come up with a function that actually satisfies this equation. So let's begin. The first step, if you actually have that written down, and I hope that you do, I'm going to actually refer to this list right here. The first thing we're going to do is we're going to, instead of writing as dy dx, we're going to write this as dx dt plus 3x equals 0. This term here, this telling you that x at 0 equals 5, the name of that in math is the initial condition, meaning it's the condition, it's the thing that lets you know exactly what c is for a particular problem after you take the antiderivative. Okay, so we don't use that yet, we use it later. The next thing, we're going to go ahead and separate variables. So we have dx dt equals negative 3x. Continuing on, we're going to say that dx over x equals negative 3 dt. Now, we're going to write integral signs on both sides. Like this. Just to double check, we've done step 1, step 2, step 3. Now let's take our antiderivatives. So we're going to say the natural log of x equals negative 3 times t plus c. And now we are ready for the next step, which is solve for c. And I'm going to add a little thing here, which is using the initial conditions. So we're going to say the natural log of x, which at 0 is 5, equals negative 3 times 0 plus c. Continuing on. Now that we know what c is, I'm going to actually, so I know that natural log of 5 equals c. So check this out. Now I can put these two things together right here and say the natural log of x equals negative 3t minus the natural log of c. Sorry, plus the natural log of 5. Now I'm going to subtract the natural log of 5 from both sides, so that's ln x minus ln 5 equals negative 3t. Now we're going to use a log rule. The natural log of x over 5 equals negative 3t. Let's take the exponential of both sides. So we get x over 5 equals e to the negative 3t. Finally, we obtain that x of t is 5e to the negative 3t. So if you plug this into the differential equation, you'll find two things. Number one, it solves it. And number two, it meets the initial condition that if you plug in 0 for the time, x is equal to 5. So now we'll attempt problem number 1. So here we've already separated out the variables, so we can say dx dt equals 3x, continuing dx over x equals 3 times dt. We'll integrate both sides, so we're going to get that the natural log of x equals 3t plus c. And now we plug in our initial conditions. So we're going to say that the natural log of 2 equals 3 times 0 plus c. So we get that c is the natural log of 2. And so we can say the natural log of x equals 3t plus the natural log of 2. Let's take away the natural log of 2 from both sides. And combining that with logarithm rules, we're going to get that ln of x over 2 equals 3t. Continuing, we'll take the exponential of both sides. So we have x over 2 equals e to the 3t. Finally, simplifying, x is going to equal 2 times e to the 3t. All right. Similarly, let's go ahead and take a look at number 2. And you might notice there are a couple things you can sort of predict if you look at these answers. Like you notice here, we end up getting e to the negative 3t, so it's kind of the opposite of the sign here, and this is 5 right there. So I dare say you might actually be able to predict that v is going to equal 4 times e to the 2/3 t. Let's see if that prediction comes true. Again, I'm basing it on the patterns of the solutions here. So my guess, I'm thinking when we do the calculus, we're going to get v equals v equals 4e to the 2/3 times t. Let's go ahead and see. So first, let's get dv dt isolated. So dv dt equals negative 2/3 times v. So we're going to get that dv over v equals negative 2/3 dt. Let's integrate both sides. And so we're going to end up getting that the natural log of v equals negative 2/3 t plus c. Plugging in our initial conditions, the natural log of 4 equals negative 2/3 times 0 plus c. So c is the natural log of 4. Continuing, we're going to say now we put these two ideas together. The natural log of v minus 2/3, equals negative 2/3 t plus the natural log of 4. We'll subtract that from both sides. And that's going to give us the natural log of v over 4 equals negative 2/3 t. Let's exponentiate both sides. E and ln are inverse functions, so we're just going to end up getting v over 4 equals e to the negative 2/3 t. And let me make absolutely sure I got that right. So I was a little off. I had my sign wrong. So this was not the best way to go. So V equals 4e to the negative 2/3 t. Excellent. All right, this seems like abstract math, but we're going to be putting this to use in circuits in just a little bit.